Hi, my name is Mella. I am a PhD student at the University of Sheffield. My presentation is about a single cylinder subjected to vortex-induced vibrations, estimating cyclic stresses for fatigue assessment. Professors Brevis and Susmel are also part of this research. First of all, what is vortex-induced vibrations, or VIV? Consider a two-dimensional cylinder with an incoming flow velocity u. As the flow moves around the cylinder, vortices are generated behind it. This process will induce fluid forces on the cylinder, potentially triggering a response, changing the flow around the cylinder, and thus changing the fluid forces to begin with. This constant feedback process refers to vortex-induced vibrations. Here we have a numerical simulation of the phenomena, where a cylinder is oscillating at a certain amplitude and frequency, and behind it, vortices are constantly being shed. In general, problems related to vortex-induced vibrations usually occur over long periods of time. It could produce instabilities in, for example, a bridge or a chimney, or induce fatigue damage. Thus, it is critical to consider this phenomena, especially in long and flexible structures. In this presentation, I will introduce some preliminary results of a cylinder subjected to vortex-induced vibrations. The first goal is to measure the cylinder response using non-contact techniques. This is very important since we want to avoid sensors on the cylinder and thus changing its dynamical properties. After that, we want to estimate and characterize the maximum stresses on the vibrating cylinder. Experimental setup. Here is an overview of the experimental setup. A cylinder is placed inside a water channel, and a camera is mounted looking at the top of the cylinder. In this particular experiment, the cylinder response was recorded at 8 different flow velocities, with a constant water depth of 24 centimeters. Here is a close-up of the structure. It is composed by an acrylic cylinder with a 2 centimeter diameter and a 30 centimeters length, a rod made of stainless steel 316 with an 0.16 centimeters diameter and a 16 centimeters length, and a rigid connection between the cylinder and the rod. The structure is fixed at the bottom of the water channel, while the other side is free to vibrate. Under this configuration, we can see that the flow will interact with the cylinder, while the resistance of the whole structure is given by the rod and the position of the rigid connection. Also, we can test the behavior of different materials just by changing the rod. So, how do we go from recording the cylinder motion to estimating the stresses on the rod? Here we see that the cylinder is reacting to complex pressure distributions. The cylinder motion is transferred through the rigid connection to the rod. From this single region of contact, it is easy to calculate the reaction moment at forces, and thus we can estimate the maximum stresses on the fixed end of the rod. Before measuring the cylinder response, we need to check that the structure moves as a single unit. We tracked simultaneously the rod, cylinder, and rigid connection under a unidimensional displacement, and in water while the cylinder is being subjected to vortex-induced vibrations. We recorded the motion history and calculated the frequency spectra. We can see that there is almost no differences between graphs, confirming that each part of the structure moves as a single unit. We also modeled the cylinder. We applied different unidimensional displacements and calculated the reaction moments on its fixed end. We observed a direct relationship between the cylinder displacement and the reaction moment. Combining the previous results with these ones, we can say that, first, the structure moves as a single unit. Second, and because of that, there is a direct relationship between the cylinder motion and the moment and forces on its fixed end. These parameters will be used later to estimate the maximum stresses on the fixed end of the rod. After the preliminary test, we put the cylinder in the water channel and recorded its motion at different flow velocities. Each measurement was performed with a high-speed camera at 70 images per second for 1 minute and a half. Here is an example of a raw image taken with the high-speed camera. Each raw image was calibrated to correct for possible inclinations between the camera and the cylinder, and to move from pixel to real-world coordinates. Finally, with the corrected images, we tracked the cylinder motion using digital image correlation. Here we can see an example of the cylinder reacting to the flow alongside the tracking of its motion. Experimental results. The cylinder motion can be decomposed into three components: a constant displacement in the flow direction, given by the static pressure of the flow along the span of the cylinder, and the oscillating amplitudes in the x and y direction, given by vortex-induced vibrations. The maximum value of these amplitudes is given by the average of the highest 10% of the recorded response. In the first graph, we have the constant displacement results, with a maximum recorded value of 0.55 diameters. Next, we have the maximum oscillating amplitude in the x direction, which has a maximum value of 0.28 diameters. Lastly, the maximum oscillating amplitude in the y direction, with a maximum value of 0.88 diameters, which is roughly speaking 3 times higher than the maximum amplitude in the x direction. From the research literature, it is expected that if we keep measuring the cylinder response at higher flow velocities, we will eventually see a reduction in the maximum amplitude. This is due to a desynchronization between the generation of vortices around the cylinder and its response. Unfortunately, we are currently limited by the maximum flow rate of the water channel to observe it. This graph shows the oscillating frequency of the cylinder across the tested flow velocities. The oscillation frequency in the x direction ranges from 4 to 7 Hz, while the frequency in the y direction is almost half throughout the measured flow velocities. In general, we can say that in the y direction you have higher displacements and lower frequencies compared to the x direction. This gives an indication that both directions could be important for fatigue damage. This graph shows the trajectories traced by the cylinder across different flow velocities. We observe that as the cylinder motion increases, its trajectory becomes more coherent, resembling a crescent shape. Given a certain cylinder motion, we can estimate the bending stresses on the fixed end of the rod using this simple equation. Here we show the results of applying this formula. In this graph, we have the maximum and minimum stresses in the y direction. It shows that the stresses are almost symmetrical, with a maximum stress magnitude of 160 megapascals. This graph shows the stresses in the x direction. These values were calculated considering the combined effects of the mean displacement of the cylinder and its oscillating amplitude. Here, the maximum stress magnitude is approximately 150 megapascals, which is a little bit lower than the maximum stress in the y direction. Finally, we calculate the stress ratio, defined as the ratio between the minimum and maximum stresses. We observe that the stress ratio given by the oscillating amplitude is fairly constant at -1, which is expected given the oscillating nature of the vibrations. When the mean displacement is added to the oscillating amplitude in the x direction, the stress ratio ranges from 0.2 to 0.4. In conclusion, the use of recording and tracking techniques can effectively measure the cylinder response. The cylinder configuration can be used to estimate the stresses of a material on VIV. The experimental results show that the motion in the y direction has higher displacement with a lower frequency compared to the oscillations in the x direction. Also, when the mean displacement in the flow direction is considered, the maximum stresses in the x direction are comparable with the maximum stresses in the y direction. As a consequence, the oscillation frequency and stresses in both directions should be considered for fatigue damage assessment. Thank you very much for listening.